Hey everybody, welcome to the first supplement for week 4 on 14.5, the chain rule, finishing up a couple of problems that we had skipped over or done part of in class. So quickly recall the chain rule here. I've written it in the more general version, the n to 1 and n to k versions. So suppose that z is a function of x1 through xn, where the xi's are functions of only t. So here we have our schematic. We have f, or z, depends directly on x1 through xn. And these all depend only on our independent variable t. So only one independent variable, but a bunch of intermediate variables here. Then our chain rule is dz dt. Again, we think of z or f as only being ultimately a function of this one variable t. So this is a regular derivative that's equal to partial of f with respect to x1 times dx1 dt, because again, x1 is only a function of t. So we're following this path for this first term. And then we just iterate down all of the paths that take us from f over to t, going term by term. And similarly, the chain rule n to k, so to speak, where we have n intermediate variables. So f depends directly on x1 through xn, but also our intermediate variables depend on several independent variables, t1 through tk. So here x1 depends on all of these, as does x2 and as does xn. So now when we take a derivative of z, we have to take a partial with respect to one of its independent variables, t sub I. And again, the formula on the right looks pretty similar. We just iterate through all paths from x to t sub I through these intermediate variables, the xi's. Okay, so example 5, if u equals f of xy and x equals r cos theta and y equals r sine theta, we showed this in class, this first relation here with the first partials. And we showed that these were the first partials, which we'll use for this next exercise. So for this exercise, we want to show this relation between the second partials. In other words, if I have a problem, say a partial differential equation phrased in rectangular coordinates x and y, maybe I would like to rephrase it in polar coordinates in some situations, r and theta. How would I reframe that problem in r and theta? Okay, so let's take a look here. We need, we saw up above, the way that we approached this was we said that the partial of u with respect to r, say, was partial of u with respect to x, partial of f with x with respect to r, plus partial of u with respect to y, partial of y with respect to r. And these derivatives were easy to do. I suppose it's, not impossible to do it the other way, to look at partial of u with respect to x as being partial of u with respect to r, partial of r with respect to x. But again, taking, say, partial of r with respect to x and y, that's not going to be a very nice derivative to do. So we're going to approach it this way. Okay, so what do we need to do down here? So down here, we want to continue on with this theme. I want to look at the right-hand side. I want to compute URR, U theta theta, and we already have UR. And then I want to show that the right-hand side all kind of boils down and simplifies to just UXX plus UYY. Okay, so we've already got UR, so we don't need to calculate that again. but let's work on URR. So that's the partial with respect to R of du dr, of the partial of u with respect to R. Or that's the partial with respect to R of this function. Now keep in mind our dependencies here. So u depends on x and y directly. And then my independent variables are r and theta. And x and y both depend on both r and theta. So taking the partial with respect to r of all of this, well, I don't see any r's explicitly, but there's kind of the implicit dependence on r through the ux and uy functions. So what's this going to be? This is going to be partial with respect to x of ux cos theta plus uy sine theta, partial of x with respect to r, let's say theta, plus the partial with respect to y of this function, times partial of y with respect to r. Okay, so partial with respect to x of ux cos theta, that's just uxx cos theta. Partial with respect to x of uy sine theta is uxy sine theta. I'm not being super careful about the mixed subscripts. We're going to assume that that u is nice enough that uxy equals uyx. And then we have partial x with respect to r, which coming up here is just cos theta. And then something similar over here. Partial with respect to y of ux cos theta is uxy cos theta. Partial with respect to y of uy sine theta is uyy sine theta. And then times partial of y with respect to r, which is just sine theta. And all of this boils down to uxx cos squared theta. That takes care of this term, plus uyy sine squared theta. And then we have 1 and 2 of these uxy sine theta cos theta terms. And that is what URR is. Again, we have UR already. And now we need U theta theta. Okay. Hoping I can keep all of this kind of on the screen here. U theta theta is going to be a little bit more involved. Of course, this is just partial with respect to theta of U theta. Or this is partial with respect to theta of negative ux r sine theta plus uy r cos theta. And here we might be tempted to do basically the same thing we did above and just say that this is something like, you know, uxx r squared sine theta and uyy r squared cos theta and a mixed term, but we have to be a little bit careful here because up here, when we took the partial with respect to r, we didn't actually explicitly see any r's floating around. But here we're taking the partial with respect to theta of this function, and we do see some explicit thetas, as well as kind of some implicit thetas through the dependence from u. So we got to be careful here. We have a product rule coming into play in each of these terms. Okay, so let's do this first term first. So this is going to give me what? This is going to give me, I guess, a negative r du dx times partial with respect to theta of sine theta. That is just cos theta. So that's differentiating the sine theta bit. And then plus negative r sine theta times partial with respect to theta of ux. And we're going to leave that there for just a minute. So this takes care of that first term. And now we have a second term. So we have plus partial with respect to theta. We'll differentiate the cos theta first. So this gives me a negative r uy, sine theta. The cos theta differentiates to negative sine theta. And then we have an r uy that don't get differentiated on this first pass, this first term of the product rule. And then we have a plus r cos theta times the partial with respect to theta of uy. Okay, so now we need to find the partials with respect to theta of ux and uy. So let's come over here off to the side and do that because I'm quickly running out of room. So what's the partial with respect to theta of ux? Well, u depends on x and y and therefore r theta, and so does ux and uy. They have the same dependence, the same schematic. So this is going to be what? It's going to be the partial with respect to x of ux, partial of x with respect to theta, plus partial with respect to y of ux, partial of y with respect to theta. Partial with respect to x of ux is just uxx. So that's good. That's a piece that we were hoping is going to pop out here and help us out with some of the cancellation. And then partial of x with respect to theta, again, from all the way up here, partial of x with respect to theta is negative r sine theta. And then plus partial with respect to y of ux is uxy times partial of y with respect to theta, r cos theta. So this is what partial with respect to theta of ux is. And what's partial with respect to theta of uy? Well, it's going to be pretty similar, right? Uy depends on x and y, and through those on theta. So it's partial with respect to x of uy, partial of x with respect to theta, plus partial with respect to y of uy, partial of y with respect to theta. This gives me uxy. Partial of x with respect to theta is negative r sine theta, plus uyy. Partial of y with respect to theta is r cos theta. Okay, so I can zoom out just a touch here. When I come over to this left-hand side, let me also get a little more room here. Okay, so this equals negative RUX cos theta. We got that term minus RUY sine theta, that's that term taken care of. Now let's look at this term. I have a minus r sine theta times all of that. So this gives me a minus r sine theta times minus r sine theta is plus r squared sine squared theta uxx. And then minus r sine theta times r cos theta is minus r squared sine theta cos theta uxy. And then this last, so that takes care of this blue term. And then the last term that we need to deal with is this last red term, which is r cos theta times this stuff over here. So this is going to give me a plus r squared cos squared theta uyy. And then I have a plus r cos theta times minus r sine theta. So that's a minus r squared sine theta cos theta uxy. Okay, so we have these 6 terms here for u theta theta. So u theta theta is going to be the first partial terms minus r ux cos theta minus r uy sine theta. And then what? Plus r squared sine squared theta uxx. So we got these, we got that one. Plus r squared cos squared theta uyy. And then a minus 2r squared sine theta cos theta uxy. Okay, and then what is the relationship that we're looking for? We'll just pop this down here. So I need a 1 over r squared u theta theta. That gets rid of that guy, and that guy, and makes this into a 1 over r factor in both of those terms. Plus, we need to add urr. What was urr? That was this stuff up here, uxx cos squared theta, or cos squared theta uxx, plus sine squared theta uyy, and these all go together. So let me put a line there so they don't get mixed up. And then plus 2 sine theta cos theta uxy. I think we're starting to see where some of this is going to end up canceling. And then lastly, we need a plus 1 over r ur. And what was 1 over r ur? Well, that's 1 over r ux cos theta plus 1 over r uy sine theta. And we see that when we add all of this together, this minus 1 over r ux cos theta goes away. The minus 1 over r uy sine theta goes away. The minus 2 sine theta cos theta uxy, that cancels with the similar term from the urr bit. And lastly, we have uxx times sine squared theta plus cos squared theta plus uyy times sine squared theta plus cos squared theta. All of this just equals uxx plus uyy. And that was exactly what we wanted to show. Again, up here, it's super easy to forget about this chain rule and end up missing these 2 terms. And if you did that, what would you end up with? If you had made that mistake in, sorry, not the chain rule, the product rule. It's easy to miss the product rule. Forget about these two terms. Well, down here, this 1 over RUR is what ended up canceling off those two terms that came from the product rule. So you'd get to the end and you'd have a bunch of cancellation, but you'd have this extra 1 over RUR that wouldn't seem to cancel anything. So that would be kind of, in this problem, the hint that you got something incorrect. But again, we were careful. We went through all of the details step by step, really carefully. And I think that made the need for the product rule a little bit more obvious than if we had rushed through. Again, we didn't need the product rule here because we don't have any dependence on R other than through the UX and UY. If we had, say, a UX R cos theta and a UI R sine theta, we would have needed a product rule here as well. Okay, so let's look now at exercise 6, looking at homogeneous functions. We say that a function f is homogeneous of degree n if it's true that f of kx, ky, kz equals k to the n f of x, y, z. So in other words, if we can factor a constant multiple of all the variables out of the function, and it comes out with a power n. So think of something like x squared plus y squared plus z squared being homogeneous of degree 2, or like square root of x squared plus y squared plus z squared being homogeneous of degree 1. Right. So another way of looking at it is if we stretch the input vector by a factor of k, the output gets magnified by a factor of k to the n power. Okay. So first, let's show that if f is homogeneous of degree n, then the partial of f with respect to x, that function is homogeneous of degree n minus 1. And I think I'll just split these up this way. Okay, so we have that that f is homogeneous of degree n. So we have this, and we want to show fx is homogeneous of degree n minus 1. Okay, so how can I do this? Well, I think this the goal here suggests that maybe we should take the x partial of both sides and see what happens. So if we take the partial with respect to x of the right-hand side, this pretty clearly is just that. So right-hand side, not hard at all. The question is, how do we take the x partial of the left-hand side? Okay, so for my left-hand side, we note that f is a function of kx, ky, and kz. We could make other variables, say u equals kx, v equals ky, and w equals kz. And we could rewrite this as the partial with respect to x of f of u comma v comma w. You could think of it this way. And now what's our schematic relationship? We have f, depending on these intermediate variables, u, v, w, and those depending on x, y, and z. Note that u depends on x, but not y or z, and similarly for v and w. So there's not like, it's not like all of the intermediate variables depend on all the independent variables. So what can I say here? I can say that, well, this is the partial with respect to u of f times partial of u with respect to x plus, and I'll just write this as fv partial of v with respect to x plus fw partial of w with respect to x. Now, what is partial of v with respect to x? Well, v only depends on y. It's independent of x. If I move x, v doesn't move at all. That's 0. As is partial of w with respect to x. W also doesn't depend on x. So really the only first term that that carries on is the partial with respect to u, or the partial with respect to the first variable, f of uvw times partial of u with respect to x. Or we could write this as partial of f with respect to x, again, being careful that when we say df dx, we're talking about the first variable, not necessarily the entry into that first variable. And then here u is kx, v is ky, and w is kz. And then what's the partial of u with respect to x? Well, here we do have times k. So taking the partial with respect to x of the left-hand side gives me this. I see then that I can combine these together and see that partial of f with respect to x of kx, ky, kz, if I divide the k over, is k to the n minus 1 power fx of x, y, z. In other words, for my function, partial f with respect to x, if I multiply each of the inputs by k, I can, in a sense, factor that k out, but it comes out as a k to the n minus 1 power, not as a k to the n power as it did in the original, original function up here. So indeed, the x partial is homogeneous of degree n minus 1, and as a very similar argument would show, so is the y and the z partial. They're also homogeneous of degree n minus 1 for by essentially the same calculation. Okay, for part B, we now want to show that if f is homogeneous of degree n, then x fx plus y fy plus z fz equals n times f. So again, we have f being homogeneous of degree n, so f of kx, ky, kz equals k to the n f of x, y, z. Okay, so what is our goal here? Well, we want to show that these partials on the left all end up as just n times f. If I look at my equation for my homogeneous function f, the only place that I see an n is in the exponent of k to the n. And I note that on my right-hand side, I need something that looks like n times f. So if I, kind of make an educated guess, how can I get an exponent down? Well, it might be really nice to differentiate this relationship with respect to k, the variable k. And we'd be thinking of k as a variable here. If I differentiate it with respect to k, that gives me nk to the n minus 1, and that gives me kind of an n times f, something going on here. So can we make that work? Well, to make that work, I need to think of k as the variable, or really the independent variable. So I have f being related to u, v, and w, where u is kx, v is ky, w is kz. And we're thinking of u, v, and w as being functions of k, the independent variable. So how does this end up working? Well, if I take d by dk, now k is the sole independent variable, so this is going to be a regular derivative. Of f of kx, ky, kz. That's going to be equal to d by dk of the right-hand side. F of x, y, z doesn't have any k, so this is nk to the n minus 1, f of x, y, z. Now I see that I can evaluate this maybe at k equals 1. That gives me an f on the right. If I can figure out what the left is, d by dk of f of kx, ky, kz, then I should hopefully be able to get my relation whenever I simplify the left-hand side and plug in k equals 1. So let's work through that. So what's d by dk of f of uvw? Well, that is partial of f with respect to u times du dk plus partial of f with respect to v times dv dk plus partial of f with respect to w times dw dk. Or this is partial of f with respect to u du dk, thinking of k as the variable here, is just x. Is just x. And then I have partial f with respect to v times dv dk, which is just y. And partial f with respect to w, dw dk is z. If I evaluate this at k equals 1, I just see that u equals x, v equals y, and w equals z. So at k equals 1, I have d by dk of f of u, v, w. In other words, d by dkf of kx, ky, kz equals df dx times x plus df dy, y plus df dz, z. One little side note, when I say something like partial f with respect to u here, I'm thinking of this as being evaluated at uvw. Or in other words, it's partial f with respect to u of kx, ky, kz. Down here, whenever I plug in k equals 1, I'm thinking of this fx as being partial of f with respect to x at, well, when k is 1, I'm just inputting x, y, z. So a little side note there on what the arguments are, because obviously it would be quite a big mess to write out all the arguments explicitly. But I do see that at k equals 1, I have my left-hand side is x fx plus y fy plus z fz, all evaluated at just xyz. And my right-hand side at k equals 1 is just n f, also evaluated at xyz. And that's exactly the relationship that I wanted to get. Okay, and then lastly, looking at a couple examples in implicit differentiation. So example 8 here, we computed partial z with respect to x in class, but let's look at a couple related ideas. So just really quickly, let's go back through and compute partial of z with respect to x. We said that we have x, y, z equals 0, where we're thinking of z is some function little f of xy. So I'm thinking in this case of x and y as being my independent variables and z as being dependent on those. And then I said that from up here, the partial of z with respect to x is the partial of big F with respect to x over the partial of big F with respect to z, and with a negative sign. Be a little bit careful here. It might be tempting if we think of z as like little f of xy, it might be tempting to somehow try to, when we take partial f with respect to x, try to do something with z there. Or when we take partial f with respect to z, wonder like, wait, how do I handle that z? Remember, when we talk about partial derivatives, when I say partial of big F with respect to x, I'm saying of the first argument, x. So with respect to these variables. So partial of z with respect to x is negative. Partial of big F with respect to x is, well, that's the derivative of e to the xy is e to the xy times the partial with respect to x of e to the xy. So this is like constant times x or y times x. That constant multiple comes down. Sine of xz, that has x's in it. It has an x as the first factor in the argument. So differentiating that with respect to x give me a plus cos of xz times z. And then the plus y, that doesn't have any x's in it. So it differentiates to 0. And then divided by partial of f with respect to z. I don't see any z's in the first or the third term of f, so those differentiate to 0. Again, we don't try to do something funny with the x's and y's or anything like that. There's no z in the first or third term. Those differentiate to 0. Sine of xz differentiates the cos of xz times x. Again, because now z is the variable, x is a constant, so the chain rule pops out another x. So what about partial of z with respect to y? The process is going to be pretty similar. Here I see a y in the exponential term, and in this third term, no y in the sine of xz term. So I differentiate e to the xy with respect to y. That gives me e to the xy times x. And then I get the second term differentiates to 0, and the third term differentiates to just a plus 1. And I divide by partial f with respect to z, which is the same as it was before. So if I envision this as f of x comma y comma little f of xy equals 0, this is kind of sensible. I choose X and Y as my independent variables. I can choose those any way that I want. And then that constrains what Z has to be. Okay, so what about partial X with respect to Z? I mean, on one hand, this is just kind of trivial. I just switch the roles of X and Z here, which just switches their roles here. So partial of X with respect to Z, we might just say, well, that's just minus partial F with respect to Z over partial F with respect to X, or it's just 1 over partial of Z with respect to X. And practically speaking, that is what it is. But note that there's a subtle change here. Here we're thinking of f of stuff being equal to 0. But if we're looking at partial of X with respect to Z, well, Z, we're now treating like an independent variable. We can choose Z however we want to. Y is also really not mentioned, so it's an independent variable. And then X here, this is what we're thinking. X is some other function of Y and Z. So in this perspective down here, we're thinking of Y and Z as being the independent variables and those constraining X. Whereas up here, we're thinking of X and Y as being the independent variables and those constraining the possibilities for Z. So in a sense, it's, procedurally not very difficult to switch from partial of Z with respect to X to partial of X with respect to Z, but conceptually, I think there's a little more going on in the background than we might appreciate at first glance. Okay, and then example 9, let me copy down the formula here. So for example 9, we want to prove the so-called cyclic relation that if big F of xyz equals 0, then partial x with respect to y times partial y with respect to z times partial z with respect to x equals -1. And we're going to use this relation. We're, of course, assuming that, the partials that can't be 0 aren't 0. Yeah, so we're not dividing by zeros or anything like that. So we see that partial x with respect to y. So here we're thinking of y and z as the independent variables and x is the dependent. Well, that's negative partial f with respect to y divided by partial f with respect to x. Partial y with respect to z, now taking the perspective that x and z are the independent variables, y is the dependent variable. This is negative partial f with respect to z over partial f with respect to y. And then partial of z with respect to x equals negative partial f with respect to x over partial f with respect to z. And we multiply these all together, we see that partial f with respect to z divides out, partial f with respect to x divides out, partial f with respect to y divides out, and we get -1 multiplied by itself 3 times, which of course is just -1. Now we have to be a little careful. We're sometimes tempted to do things just like, canceling differentials, treating them like they're fractions, but we notice that if we did something like that up here, we might be tempted to just cross out these partials, cross out those and cross out those, and we would think that everything is +1. So that's not really a valid thing to do. Sometimes it can lead us to an idea that might be valid and that we can carefully construct a proof around, but we don't want to go too far with that. We don't want to take too many liberties with doing things like that. Okay. And then working off of example 9, let's actually work with a specific function, the ideal gas law, f of PV and T equals PV minus nRT equals 0. And here N and R are constants. So let's take a look at this and let's try to show this relation up here, or in other words, let's try to show partial of P with respect to V times partial of V with respect to T times partial of T with respect to P equals -1. And of course, I mean, we could just compute these partials and they all divide out, but let's do this a slightly different way than what we just went through. So if I look at partial of P with respect to V, I'm thinking of V and T as the independent variables and P as the dependent. The nice thing about a fairly simple function like this, even though it's written implicitly, it can pretty easily be solved explicitly for anything we need. Whoops, I missed the partial sign there. So we can write P explicitly as a function of the independent variables T and V, like this. And then, of course, the partial of P with respect to V is, so this is V to the -1, this is minus nRT over V squared minus nRT V to the -2. And I'm going to choose to write that as minus P over V. nRT over V equals P, as we just saw. So this is minus P over V. Partial of V with respect to T, well, V's relationship with P is very similar, right? Just move the nRT over and divide by P instead of V. So the partial of V, but now we're taking the partial with respect to T, not P, so we have to be a little careful here. This is nR over P. And what's the partial of T with respect to P? Well, how do we get T in terms of everything else? Well, T is PV over nR. Keep in mind, N and R are constant. Partial of T with respect to P is just V over nR. And I see I get a lot of cancellation. My V's go away. My P's go away. My NR's go away. And I'm just left with -1. So I've verified this in a different way than this kind of abstract reasoning up here. I've shown, I think, pretty clearly that this holds, the cyclic relation holds in this case. Okay, so that wraps up our discussion of the chain rule. I think similar to the chain rule in Calc 1, the chain rule can be a sticking point in Calc 3. So, go through the problems on WebAssign, do the practice problems, drill them, make sure you're comfortable with this, because it will come up throughout the course. Okay, but that finishes us up for this supplement.